Hello and welcome to Lab 3 of Physics 2. Let's get started. In this lab, we're going to be calculating the magnetic field of a bar magnet at parallel, perpendicular, and off-axis locations. And our purpose is going to be to observe the relationships in the dipole magnetic field formula between position, distance, and the magnetic dipole moment, as well as visualizing the magnetic field with a model. Our final results preview is that the magnetic field that we calculated in the spreadsheet is going to be 71.9 or so microteslas. In the computer model, it's closer to 27. We're going to be discussing towards the end why these values look a little different. Some of the physics principles that we're going to be using, first of all, is the magnetic field of a dipole at observation location R. This is going to be important for our computer model when we're trying to calculate this magnetic field at different locations. And these three formulas are going to be used together when we're trying to find mu for this, so we can plug into this formula. In this experiment, we used a magnetometer on our phone to calculate the magnetic field at different observation locations around the magnet. And we're going to consider our phone sensor to be the system because it's going to be experiencing the magnetic field or the magnetic force from the Earth's magnetic field and from the magnet. And lastly, we recorded the X components of the magnetic field at parallel locations from the magnet, and then recorded the total magnetic field at an off-axis observation location. Here we have our experimental data where we record the average distance as well as the average X component of the magnetic field at each of the observation locations. We take the natural log of these measurements and plot them on the graph, and it shows that there's an exponential relationship between the magnetic field and the distance, or the magnetic field X component and the distance. And that factor appears in our graph to be a negative 3.48, which will look very similar to our factor of 3 in this equation, as you can see. So, or negative 3 because it's in the denominator. And then we have our off-axis location magnetic field measurements here, including our net magnetic field of 71.996. So now we take a look at our code and we see the first thing we need to do is calculate the magnitude of mu, which we can do using these equations that we referenced earlier, where we replace the area times the current in this equation with mu, and then we can set mu equal to the constant k divided by mu naught divided by 4 pi multiplied by factor of 2. Next, we have our function for calculating the magnetic field of the dipole at a given location, given both the location and what mu is, and that's going to just use this equation here for that. Further below, we have scaling for our arrows. This is all for visualization. So we have our arrows here, and then if we scroll all the way to the bottom, we calculate the total magnetic field at our off-axis location. And so when we run this, we see that the magnetic field at the observed location parallel to the magnetic dipole is twice the magnitude of the magnetic field at the observed locations perpendicular to the magnetic dipole. And the direction is also opposite. When we look at the location off-axis from the magnetic dipole, we see that the total magnetic field is about 27.15 microteslas. So now we ask the question, why does our calculation of the magnetic field in the experiment differ from the calculation done in our model? Well, there's a couple different factors that could have caused this. One being that there was an additional magnetic field that wasn't accounted for in the experiment that was disrupting our sensor. Another potential cause is that the computer model assumed no z component of the electric field, while in our experiment we did get a z component that contributed to the total magnetic field. Now, if we ask how would our results have changed if we hadn't oriented our experiment to compensate for magnetic north, really all that would happen is that the components would change. So the x, y, z, those would all be different values, but overall the magnitude of the magnetic field is not going to change. What happens if we stick two identical magnets together end to end and run the experiment again? How would we expect our measurements to differ? Since we know that magnetic fields superimpose, and we also know that the two connected magnets will have dipoles pointing in the same direction, we can simply know that our magnetic field is going to just double from what one magnet would measure at a given location from the two magnets. So in conclusion, we learned that the magnitude of an electric field along the axis of the magnetic dipole is twice the magnitude of the electric field perpendicular to the axis, given that the observation points are the same distance. And when measuring the magnetic field of an object, it's important to consider all other possible sources of a magnetic field on the observation location, because that can throw off your results. Thank you for watching.